Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
After this module, we start to specialize. Each later module addresses one specific aspect of the fieldwork or the processing or the interpretation. This is the last chance we get to take the grand view. And the grand view is important, the overall vision of the place of geophysics in the whole scheme of exploration. Let me say it out straight. Of course you want to advance your career by becoming an expert in some specialization of geophysics. But your career will advance further if you also have the grand view. And it will be much more interesting too. So let's look in more detail at that important middle ground between geology and geophysics. Let's talk first about structure, the traditional service of geophysics to geology.
To the geophysicist concerned with structure, the nature of the Earth is described by two quantities: velocity, because velocity defines the ray paths and the reflection times, and acoustic impedance, because that defines the reflection amplitudes. So velocity, then, and density.
Next, we recall from GP203 that for a given series of layers of given thickness, we can use the known velocities and densities to obtain the reflectivity series. On each spike of this series, we can erect the appropriately scaled reflection pulse and add them all together to obtain the synthetic seismogram.
Which can be on a scale of reflection time, of course, since we know the layer velocities.
Right. So from a model of a set of flat-lying layers, we can compute the corresponding seismic reflection trace.
Next, we recall that if the layers are not flat, we can construct normal incidence rays from each surface point to each reflector, and so compute the reflection response at that point. Then a number of such surface points gives us the whole seismic section.
And this simple use of rays is sufficient to alert us to a situation where several normal incidence rays are possible, so that the seismic section must not be taken at its face value.
Next, we recall that for the full picture, we must abandon the simplicity of rays and use waves. However, it's still not too bad. On every interface, we regard each point as a Huygens source, sending out its spherical wavelet back to the surface,
where it generates across the corresponding traces a pattern that we call the Huygens hyperbola, or the diffraction hyperbola.
Then we do the same for all the other points on the interface, obtain the corresponding Huygens hyperbola for each one, and add them together.
For example, if this is the depth model, with the velocity and density known for each layer, then by adding all those hyperbolas, we get something like this, the corresponding time section.
Given enough computer power, we can extend the technique to 3 dimensions, and incorporate real-world nasties like transitional reflectors and lateral variations of velocity within layers.
In fact, we can construct the near-trace seismic section for almost any Earth model, using just the velocity and the density in each layer. That's all we need for the near-trace section, involving reflection only at normal incidence. But if what we want is to construct stacked sections, where the long offset traces in each gather represent wide angles of incidence, we remember that we also need some sideways property of the rocks, either the shear velocity or Poisson's ratio.
Finally, if the reflection pulse in our synthesized sections is to show a real-world broadening with time, we must include the absorption measured either as dB per wavelength or as Q.
So, simplifying all that somewhat, we have just 4 variables: density, the 2 velocities, and Q, totally defining the Earth as the geophysicist sees it.
All this is very comforting. Given almost any set of rock layers and these 4 variables for each, we can synthesize the full stacked seismic section that we would expect to get from it. This is good. It helps us to understand why in complex zones some interfaces show and some are hidden. It helps us to design the field techniques. It helps us to check an interpretation by modeling it back to a synthetic section and comparing that with the real section. What is more, this checking concept can be made interactive. Either at the scale of a single trace or on a piece of section, we first set up some reasonable model of the Earth as we think it might be. Then we construct the synthetic and compare it with the real, deriving some number saying how well it matches. Next, we make some plausible change to the model, reconstruct the synthetic, and ask, is the match better or worse? That tells us in which direction to make the next change. Again, we reconstruct the synthetic and ask, is the match better or worse? And so on, gradually homing in on an interpretation that best fits the real data. We should not get too excited about this. The details are tricky, and the answer is neither unique nor necessarily the best. But it does illustrate that the seismic description of the Earth is a nice, tight little system. Given any configuration of layers, we need just 4 variables in each layer, and the Earth is specified in seismic terms. The layer thicknesses may vary, of course, and the 4 variables may vary within each layer, but we don't need more than just the 4 variables. We can forward model the seismic response to this Earth with confidence, and we can home in on a satisfactory match between this model and the actual observed response. Yes, it's a nice, tight little system. The problem, of course, is that our 4 variables, VP, rho, VS, and Q, are not the ones wanted by the petroleum geologist. This is where the trouble starts.
We've looked at the geologist's wish list before. Here, we just pull out of it a few of the really critical variables.
Well, it's tough, but it's not impossible. Structure, of course, is what seismics does best, provided that the interface in which the geologist is interested does generate a reflection or is conformable with one that does. We can generally map structure with confidence.
In time.
In time, and nowadays, better and better, in depth. So I'm going to say yes to structure.
Okay, now let's look at the tectonic and burial history. We remember the technique from one example of salt pillowing that we worked in GP204. We mark the major unconformities and the other major picks, noting their message of layer thinning and thickening. Then we remember we strip off the first layer by bringing its base up to the surface, and so on with each layer in turn, each such operation moving back one stage in the tectonic history, so that finally we see how it all happened.
From such a tectonic history, we can infer the maximum depth of burial of particular rock units and how long they were there. Using this example in GP204, we constructed 6 prior stages of the tectonic history, and back slowly to today. We see, of course, that the older layers are going deeper, and we now want to put this process on a time scale. Let's consider one location along this profile, say here in the trough, and go back all the way to the beginning of Zechstein deposition in the Permian.
And what we're after is a plot relating depth to geologic time, in terms of the succession Permian, Triassic, Jurassic, Cretaceous, Tertiary, or in equivalent terms of millions of years before the present.
Right. Obviously, at the beginning of Zechstein time, the base Zechstein was at the surface, depth 0, while at the end of Zechstein time, the base Zechstein was at this depth, so the base Zechstein went down more or less so.
The end of the Zechstein here is the start of Triassic, initially at 0 depth. At the end of Triassic time, the base Triassic was at this depth, going down more or less so, with the base Zechstein going on down below it.
Top Triassic is base Jurassic, which goes on down for a time, with the others below it. Very likely there was more Jurassic, and everything went down some more, but we cannot know for sure because of the unconformity. Obviously, after the Jurassic went on down, it was uplifted again, and much of it was eroded off.
So we cannot pick up the story again until the Upper Cretaceous. By the end of the Upper Cretaceous, the base is down to here, and the others appropriately deeper.
And so on. By this time, in the Tertiary, we have the base Tertiary down to here, and the others appropriately deeper.
But later in the Tertiary, when everything is down to here, we meet another unconformity, largely a consequence of the accelerated salt movement. So another gap in our plot.
And finally, we come to the present, when after some more deposition, everything is down to here. At this particular location along the line, we have a plot of the burial history of each layer, depth as a function of time.
Of course, there are some details we must attend to. Our original reflection times must be converted to depths, and we need to crank in some reasonable degree of compaction, appropriate to each rock type. A lot for the shales, less for the others. But the key question, obviously, is what we do about the gaps.
Well, from the rest of the line and from other lines, we can usually get some idea of how much further down the succession went and how much further up it was uplifted, so we can make an informed guess.
And then we have a valuable display. We can superimpose on it the local kitchen conditions that favor the generation of oil and the generation of gas.
So that if in this area there are potential source rocks in the lower Jurassic, we can see that these rocks have been in the oil window for about the last 35 million years, and perhaps for 10 or 20 million back in the upper Jurassic. We have some chance of oil from these source rocks, no chance of gas.
That's right. If we are interested in gas sourcing, we must go back into the pre-Permian.
So going back to the geologist's wish list, under reasonably favorable circumstances, I'm going to say yes to tectonic and burial history.
And half a yes, perhaps, to saturant. Not in the sense that we know that hydrocarbons are present, but in the sense that if they are present, we have a lead as to whether to expect oil or gas.
Let's look next at rock type. We have several approaches. Right now, let's concentrate on the one that infers rock type from depositional environment, in the sense that, dune sandstones form on arid land, limestones are profuse in warm, clear, shallow water, shales in the deeper offshore, sandstone bars in the near offshore.
We have seen many examples in the manual of GP204. A wedge of sediment thinning by sediment starvation, any sandstones present being likely to the right, silts and clays to the left, a pod of sediments from a local sediment source, deposited from its confused internal structure under high energy conditions, except at its toe, a fan of sediment formed against a fault scarp, again with the coarsest grain material expected closest to the source, the typical pattern of marine onlap in a period of rising relative sea level and with good sands likely close to shore, an erosional channel with potential for high-energy clastic infill, and so on.
So we ask, can we formalize the recognition of depositional environment, and from that our expectations of rock type?
Let's start with a very simple example. On the flank of a basin, perhaps a simple pattern like this.
Well now, who remembers the infamous Chapter 10 of GP203? This is what we do.
First, we pick the unconformities, recognizing them, in this case very simply, by the angular truncations. We remember not to be fazed by the occasional changes of amplitude, or even of polarity.
Okay, then these two unconformities become sequence boundaries. They divide the reflections into 3 zones, each of which has a distinct reflection pattern, representing a distinct genetic unit.
We remember also that reflections from within each such unit are generally stratal reflections from bedding planes.
And that even in zones where an unconformity itself may generate no reflection, the unconformity is revealed by the termination of stratal reflections.
Okay, now let's take the message about relative sea level. Where was sea level at the time this unconformity was being eroded?
Well, somewhere off to the right. Relatively. Very low.
And where was it later, when these sediments were being deposited?
Well, somewhere up there. Relatively very high.
And later, when these sediments were being deposited?
Down there. Relatively low again.
So when we see a pattern like this, we infer a cycle of relative sea level, from low to high to low again, and with the two sequence boundaries representing the times of low stand.
So let's graph it, relative sea level against time. Here we say low relative sea level at this time, then a rise through this value at this time, a turnover and down to this low stand at this time, followed by a rise through this value here. One sequence cycle of relative sea level.
So cycles of relative sea level obtained from seismic data.
Yes. Now let's ask what is happening to the coastline during these ups and downs of relative sea level.
The key is to look for the break in slope. At the time this interface formed, the actual situation was like so. Then the break in slope is the depositional coastal break, which commonly occurs at a water depth of about 10 meters.
So we know in what water depth the sediments were deposited. Landward of the break above fair weather wave base, seaward of it below wave base.
Here, shallow water sediments deposited under high energy conditions. If there are coarse-grained sediments available, this is where they will be.
Here, deeper water sediments deposited under calmer conditions, very likely fine-grained sediments, quite uniform.
And the coastline itself is typically several hundred meters landward of the coastal break, which marks the boundary, of course, between the shallow water deposits of the marine margin and the non-marine deposits of the coastal and alluvial plains.
So, going back to the present picture, we see that the movement of the depositional coastal break gives us the likely movement of the coastline, and thus the movement of coastal rock types.
Obviously, this is very important. From the seismic reflection pattern, we track the depositional coastal break, and hence the coastline. Then we know the depositional environment here, fluvial deposition on the coastal plain, and here, tidal flats, and here, a high-energy shallow water environment, yielding to this low-energy fine-grained deposition in deeper water.
And from the depositional environment, we can guess the rock types. Given suitable sediment supply, we expect generally undifferentiated non-marine sediments here. A good chance of sorted sandstones here, and marine shales out here, with of course a transitional tidal zone here and another transition here.
Okay, rock types from seismic reflection patterns. Let's take a more complex example.
Well, as we did before, let's start by recognizing the sequence boundaries. I see clear angular relations here, on-lap, and on-lap, and down-lap, on-lap again, and down-lap. Tracing through such points, we have a lower sequence boundary, an erosional unconformity down to here and uneroded thereafter, and an upper sequence boundary, the same. So for simplicity, let's restrict ourselves to the one sequence between these sequence boundaries. Okay, that's better. Now, let's trace the movement of the depositional coastal break starting here, the lowest place we see it, and going up and out, like so.
This outbuilding, or progradation, is telling us that the volume of arriving sediments is greater than the space made available by the rise of relative sea level. But after this, we see a dramatic change. There is retrogradation of the depositional coastal break, telling us that the relative sea level is rising faster than the sediment supply.
Then, after that, the relative sea level is again unable to keep up with the sediment supply, and we have a major outbuilding.
So that in the simple case of constant sediment supply, we have this message. During the deposition of this sequence, relative sea level rose from here to here, initially slowly, then rather fast, and then progressively more slowly again.
Of course, there's a lot more on this message in the manual, but here let's be sure to take the inferences about depositional environment and rock type.
Okay, in this illustration, the extreme low of relative sea level occurred here, accounting for the eroded nature of this sequence boundary, including the eroded valley here. At that time, the surface of the solid Earth looked like this. In fact, let's start our visualizations just a little before this, when the relative sea level was still falling, and not yet so much erosion. then the full picture might well have been like this.
On a scale of 1 to 10, let's say this is relative sea level 5.
We see the high ground far above sea level, yielding to lesser gradients, where the streams are braided but fairly straight. Then the alluvial and coastal plains, where the rivers meander. Then we see the deltas, outbuilding their sediment fans into fairly shallow water.
But if the relative sea level falls any further, any coarse-grained sediments in those deltaic fans will themselves be eroded and be transported down the slope. So if we visualize such a fall, say to level 4, the first thing we expect to see is a basin floor fan.
Which makes our eyes light up, because basin floor fans often make excellent reservoirs.
Okay. Now, the erosion continues while the relative sea level stays low. The eroded valley we saw in our original cross-section is now well developed. The Big Canyon deepens, and the products of the erosion begin to fill in the slope to form a slope front fan.
Generally of mixed sediment. Some coarse-grained materials, especially associated with those channels we see, but not showing the excellent sorting that is characteristic of the basin floor fan below it.
Now the relative sea level just begins to rise towards level 5. A rising sea level makes more space available for sediments in the valleys and close inshore. We have a low-stand wedge of sediments. The delta, coupled with the winnowing action of the waves, offers scope for sorting and cleaning of the coarse-grained sediments. And the rising relative sea level acts to preserve any such bodies of coarse-grained sediment.
Now comes the fast rise, way up to level 8. This makes available far more space than the sediment supply is able to fill. So we get a major transgressive system, with thick non-marine sediments backed up on the coastal plain, and starvation of fine-grained sediments out to sea.
So here we have generally poorly sorted sediments, except where sorting is achieved by the rivers, such as in point bar situations. The greatest scope for sorting occurs from waves at the shore face. Again, any sorted coarse-grained deposits are rapidly buried and preserved by the rising relative sea level.
Now the rate of rise decreases. The sediments can more than fill the additional space, and so the coastline regresses seaward again.
For the first time, we now have alluvial deposits here, distinct from those of the coastal plain, a high-stand system.
While we have that on the screen, let's just take note of this surface. It represents the surface of the solid earth at the time of maximum landward movement of the coastline. It is the maximum flooding surface that we looked at briefly in the GP203 manual. It looks like an unconformity, but without erosion. It is not a sequence boundary.
No. To get another sequence boundary, we need another cycle of relative sea level. That would ordinarily start with another fall, which would erode the top off these existing sediments. But just for interest, let's say that there is scarcely any fall, just a still stand, before the relative sea level rises again. Then what we can expect, as the rise starts again, is this: little or no upbuilding. Indeed, until the rise starts in earnest, there may even be some erosion of the coastal plain. All the sediment is bulldozed over the edge to form new shelf margin deposits. And this becomes the second sequence boundary, signaling the end of the first cycle of relative sea level and the beginning of the next.
Okay, between the two sequence boundaries, then, we have our original reflection pattern. But now, in our mind's eye, we see the whole train of geological events that gave rise to it. This visualization tells us the depositional environment of every piece of rock anywhere in the pattern. And so, depending on the sediment supply, the type of rock that we can expect anywhere in the pattern.
Stress that proviso.
Yes, of course. A marginal marine environment can give us coarse-grained sandstones only if the sediment supply includes coarse grains. It's a lead, not a promise. But still a reasonably good lead if we can see that the sediments are derived, say, from a large basement uplift off to the left.
Okay, so we see the scheme. We identify the sequence boundaries, each corresponding to a relative low in sea level. Track the movement of the depositional coastal break and the coastline as the relative sea level rises, and infer what kind of sediments, what rock type, is likely to be deposited where. Let's illustrate it down here.
At the beginning of the sequence, with relative sea level at a low, we hope to see the basin floor fan in this position. Often an excellent reservoir sandstone. A prime target.
Next, we remember, comes the slope front fan, generally of mixed sand silt clay composition, but with a potential for good sand accumulations in the channels, and possibly in overbank splays. So occasionally, good reservoir sandstones, but difficult to find.
Then comes the low stand wedge. Here, there's the possibility of infilling previously eroded channels, sometimes with coarse-grained sediments. But again, those things are difficult to find unless they're large. Then there is potential in the sands of the coastal belt. Landward of those are non-marine deposits of mixed composition, generally dull, but occasionally relieved by sand-filled river channels, point bars, or extensive sand dunes. While seaward of the coastal plain, of course, we expect only marine shales, potential source rocks, perhaps, but of no interest as reservoirs.
Except that at the bottom of every slope, there is always the potential of sorting by sliding, and the formation of shingled sands at the toe.
Which would take some courage to drill in that position.
Well, yes, but remember we can still do this type of analysis after the whole region has been folded and faulted by taking out the structure and unfaulting the faults. Any of these sandstone bodies may later be structurally high and a good target.
Well, that's true. Now, while we have the low stand wedge in our sights, let's just look at the detail of this potential sandstone body. First, our tracking of the depositional coastal break tells us where to drill for the greatest thickness of sandstone. Second, we can ask what is the message of reflections, such as these, within the low stand wedge.
Well, in GP203, we talked of those as parasequence boundaries. Parasequence boundaries caused by higher frequency cycles of relative sea level superimposed on the general rise between sequence boundaries.
Right. So let's look more closely and ask why we've done this.
Well, that cannot be right. For a start, the transition from sandstone to shale is gradual, not abrupt as you have shown here.
Yes, of course. This is just for diagrammatic purposes, to show more clearly the curve here and the reversals shown as coincident with the parasequence reflections.
Yes, I was just asking myself why those would be coincident.
Well, first, the very presence of those reflections within the wedge tells us that there were higher frequency cycles of relative sea level superimposed on the general rise.
Right. No such cycles, no such reflections.
Next, according to GP203, many or most stratal reflections are born at accelerations and decelerations of relative sea level. So, looking at these two reflections in particular, we can visualize relative sea level doing this: a general slow rise with a higher frequency small amplitude cycle superimposed on it, so that the velocity of sea level rise is like so, and the acceleration is like so.
Oops, that acceleration is the wrong polarity.
No, you're thinking in terms of reflection time, increasing downwards. This is differentiation against geologic time, increasing upwards.
Ah, yes, okay.
Now, each reflection that we see is therefore a doublet, composed in many cases of an initial negative reflection interfering with a later positive reflection.
I'm going to have to read the infamous Chapter 10 again. It seems to me that sometimes a thin limestone might form in there, on the shelf, in which case it would start positive and be more complicated.
Of course, we're talking only the coarsest generalizations here, and one particular type of shelf sequence. The details are subject to all manner of changes, dependent on local conditions. But let's press on to the next system, the big transgression, as the relative sea level rises rapidly.
Those new gray rocks are almost certainly shales, of course, which is good for sealing those reservoirs in the low stand wedge.
We don't have to go through the rest in detail. We can see generally, by tracking the coastal break, where the largely undifferentiated non-marine sediments are likely to be, where the marginal marine sandstones are likely to be, and where the shales are likely to be, together with all the lateral transitions between these rock types.
With fair potential for reservoirs in the marginal marine sandstones, provided that we can find a seal.
And particular potential at the zone of maximum flooding, because of the stacking of so many sandstone bodies, all testable with a single well.
Okay, let's go back to our wish list. Dare we check depositional environment?
Well, what we've been doing needs good seismic. It needs lots of seismic over at least one flank of the basin. And let's face it, sometimes the unraveling is tough. But yes, we have the tool, and we begin to make great strides.
And where we can get the depositional environment, then we have a good lead on the rock type. Not always, because it must depend on the sediment supply, but often.
Okay, so now let's ask about geologic age.
Well, what age markers could we possibly hope to identify in a seismic section? Answer: the major unconformities. For although local unconformities may be formed by local causes, by local uplift, for example, with no useful inferences about sea level, a major regional unconformity generally represents a major low stand of global sea level.
For example, suppose we see this section. We quickly identify the sequence boundaries. Then we look for evidences of where sea level was at various times. We look for evidence of coastal onlap. The earliest evidence is here. Then we see the coastal onlap rising up the eroded unconformity surface, all the way to here.
The next evidence of coastal onlap is way down here, so relative sea level must have fallen, like so. We can estimate the amount of that fall, the fall in the position of coastal onlap, as so many milliseconds, and hence as so many meters or feet. Let's suppose that in this case the answer is 350 meters. Then we know immediately from the magnitude of the fall that we are looking at a major global event. There are not many falls of 350 meters in geological history.
To find out which one it is, we graph our conclusions about the position of coastal onlap. First, we have the rise, from here to, at least, here, which we may plot like so. In fact, that's not quite right, because ordinarily this point out in the basin would have subsided more than this point. We can get some protection against differential subsidence by measuring the rise in a series of steps up the unconformity. First, a vertical rise. Then, because a stratal reflection is a surface of constant geological time, the next measure of the rise. Constant time again, and the next part of the rise. Constant time again, and the last part. The total rise, then, adds up to rather less than before.
Okay, then we have the fall, from at least here to here. We may plot it like so: 350 meters, the rise and the fall.
We can continue in the same way. From this low, the coastal onlap rises at least to here, rises to here, and so on. A fall to here, a rise, a fall, a rise, outbuilding to a still stand, and so on. The coastal onlap chart.
At this stage, the scale for the level of coastal onlap is calibrated, in meters or feet. But for the other scale, which is just a succession of events in geologic time, we have as yet no calibration.
Let's concentrate first on the rises. Then some help comes from looking at the volumes of sediments between events. During the first rise, a large volume of sediments. During the next rise, a small volume. So if the sediment supply is more or less constant, these volumes give some idea of the duration of each rise. And we can adjust the rise times on the onlap chart accordingly.
About the duration of the falls, however, this type of analysis may yield little, because the evidence is usually eroded. So with no evidence at this stage, we'll admit we don't know and concentrate on the rises. Now this obvious stillstand reminds us that some degree of stillstand must be normal before a fall. So this is a more usual appearance. We see then the typical appearance of a coastal onlap chart, except that we usually turn it to make the time axis vertical. Now, the key step. We can also do all this in an area where we have abundant well control, where we know the geologic age of each sequence. Indeed, we can do it in many such areas all over the world. From these, we can establish a master chart of relative coastal onlap, high, low, as a function of geologic age, on a scale of millions of years. Now, if we look at our chart, in comparison to the master chart, we can see that there is a local character match here. At the same scale, we see that the match is not perfect.
We would scarcely expect it to be perfect. What with variations in local sediment supply and erosion, and local variations of subsidence.
But it is enough to give us a good lead. If the same message is borne out on other lines, we grow increasingly confident that these sequences fit on the geologic timescale here. So that this big fall occurred about 60 million years ago, and so that we can date this unconformity at about 60 million years.
Very good. That's a bonus we did not expect to get from seismic data.
Indeed. So let's go back to our wish list and put a qualified yes by geologic age. It has to be qualified because there are pitfalls and doubts along the way, which we shall talk about in later modules. But nevertheless, a yes.
Fine. Now let's look at what's left on the wish list. Let's see if we can add to the specification of rock type and do something about these.
For which we must return to a matter we broached in GP202. What is the relation between a rock as a geologist sees it, for example in thin section, and a rock as we see it, that is, as a substance having a density, a compressional velocity, a shear velocity, and a Q?
The density, as we have agreed before, is easy. However many components the rock has, coarse grains, cement, fines, water, oil, the rock density is always the sum of the component masses divided by the sum of the component volumes. And in practice, since the densities of the grains and the cement and the fines are all much the same, the decisive factor is the porosity. Density goes, first and foremost, with porosity.
But velocity, we remember, is not so simple. Let's start, for a change, with shear velocity, V sub s. Any velocity, we know, is always the square root of the appropriate elasticity over the density. And for shear, the appropriate elasticity, stress over strain, is the rigidity, the reluctance to change shape. So shear velocity, V sub s, is the square root of the rigidity over the density.
Now, moving towards real rocks, our first step, as before, is the cubic packing of spheres. When we shear, each sphere changes shape, but not volume. Provided there is overburden pressure, the grain contacts do not slip. If we imagine lines drawn through the grain between opposite contacts, we see what happens. The inner part of the grain just rotates, while almost all of the shearing occurs in the outer shell, near the grain contacts.
So the rigidity, and hence the shear velocity, depends on the way that the cross-section of the grain thins as it approaches the contact. Thus, this mythical but very angular grain would have small rigidity. The contact zone would bend very readily and allow the central zone just to rotate, whereas the sphere is less bendy near the contact. Greater rigidity, higher shear velocity.
But there's a change of porosity also between those two.
Yes, but it is not the change of porosity as such that is changing the shear velocity. A grain like this, fanciful though it may be, illustrates the point. It has the same porosity as the sphere, but lots of give in the contacts. Small rigidity, low shear velocity.
So with more realistic grain contacts, a lot depends on how the grains thin as they approach the contact. We must brace ourselves for some dependence of shear velocity on the angularity of the grains.
Except that this dependence can be lessened by modifications to the contact. For example, at shallow depth, an angular contact may look like this, being very bendy near the contact. At greater depth, with the contact compressed, the flexibility is much reduced. The shear velocity increases with compaction. Cement has a large effect at shallow depth, but less at great depth. And if the compaction is sufficient to cause solution and recrystallization at the contacts, then the original flexibility is very much reduced.
And opposite effects. Here's a rounded contact at average depth. Not much flexibility in that flattened contact. But the same contact in the presence of overpressure becomes more bendy. Reduced shear velocity.
Let's see what else affects shear velocity. Well, the number of contacts per grain, that's important too. If we hold the grain in place at more points, resisting deformation, the rigidity increases, and the shear velocity with it. So if we go from this cubic packing of spheres to this more efficient packing, the shear velocity increases. not because the porosity has decreased, but because there are now 12 contacts per grain instead of 6.
How about the saturant? How does that change the shear velocity? Well, not much. Since the volume of the grains does not change, the volume of the saturant does not need to change either. Only the shape changes, and fluid saturants offer no significant resistance to change of shape. So we have a picture of the shear wave passing through the rock from grain to grain solely at the grain contacts, with the fluid saturant not really participating in the wave. In effect, the fluid in the pores is just dead weight, to be dragged from side to side as the wave passes. As such, it affects the shear velocity only slightly, through the density rather than through the rigidity.
What if the pores also contain loose fines, loose clay particles? Well, if there are few, again, they make no difference to the rigidity, only a slight difference to the density, thus decreasing the shear velocity. And if there are many, a larger decrease in the shear velocity because of density, but the beginnings of an increase only when the fines really start to hold the grains in place, to resist their change of shape. Overall, not very much effect.
Except in those depositional or diagenetic situations that actually get clay into the contacts. Then the contact rigidity can come zooming down, and the shear velocity with it.
So let's summarize. What geological factors control shear velocity? The really big one first, cementation. The presence of cement swamps other factors. If the rock is not cemented, and only then, grain shape and grain sorting become major factors because of their effect on the flexibility and number of the grain contacts. So does depth of burial for the same reasons.
Now, the second-rank factors. Rock type. My goodness, look at that. The type of grain itself only of second rank. And the clay content. Small amounts of clay actually decreasing the shear velocity.
And finally, the minor factor, the type of fluid in the pores. Again, only because of its slight effect on density.
But one rock property that is not on the list is porosity. Not with any clear relation, and that's because, as we've seen, the pores do not really have much to do with it directly. It's the contacts that matter. Only insofar as porosity goes with grain type can there be any loose relation. And even then, just a little cement, having little effect on porosity, can have a dramatic effect on shear velocity.
Okay, now let's have a look at compressional velocity. As always, the same basic equation. Now, however, instead of just rigidity in the numerator, we have both the rigidity and the bulk modulus.
We remember why this is. When we apply the stress, the resulting strain involves both a change of volume and a change of shape. The reluctance to change shape is still the rigidity, as before. The reluctance to change volume is the bulk modulus. So both enter the compressional velocity.
Well, we can follow the same route. The cubic packing of spheres, as it participates now in a compressional wave. First, we notice something that is definitely different. That is, that in addition to the grains getting squeezed, the fluid in the pores gets squeezed also. Thus, in a compressional wave, it's not just the grains carrying the wave. The saturant contributes also. So while the saturant has little effect on the shear velocity, it may have a significant effect on the compressional velocity. In particular, we remember the presence of just a tiny amount of gas in the pore can send the compressional velocity down. And if there are few grain contacts and little cementation, can send it way down.
By the same token, fines in the pores have a different effect for compressional and shear. In shear, loose fine particles are just dead mass to be dragged from side to side, decreasing the shear velocity. In compressional, they make their own contribution to the reluctance of the pore fluid to be compressed, and so increase the compressional velocity.
Again, unless there is gas in the pore. But let's put the rest of that discussion in the manual and go on to the factors that are similar for compressional and shear. In shear, we have said, the grains change shape, but not volume, and the contacts are critical because they oppose those changes of shape. In compressional, the grains change volume. The contacts are again critical because they oppose this change of volume, forcing the grains to change shape also, to bulge into the pores.
And all the things we've said about the contacts for shear apply much the same for compression. Overburdened pressure broadens and stiffens the contacts. So does cementation and pressure solution. and so on. It's all much the same, and the potential for changes of volume and changes of shape is reduced if we increase the number of contacts per grain.
Okay, now let's go back to thin sections and to our attempt to visualize velocity geologically. In particular, let's see if we can find some way of expressing that ability of the contacts to oppose both changes of shape and changes of volume. A way that includes not only the broadening of the contact under overburden pressure, but also the effective broadening by cementation.
Well, my suggestion would be a measure like this: supported grain surface over total grain surface.
Well, maybe. Supported over total. Yes, maybe that would do it, until I can think of something better.
This, then, would be a master variable, expressing the contact properties of the grains. This would be the link between the thin section and the seismic velocity.
Okay, let's see how it would work. The shear velocity would depend, first and foremost, on your master variable, supported area over total. Then it would also depend, of course, on the intrinsic rigidity of the grain material, but not on much else.
Right. While the compressional velocity would also depend on, let's say, the same master variable, plus the same rigidity of the grain material, plus the bulk modulus of the grain material, plus the bulk modulus of the saturant.
Well, that's a simplification, of course. Both velocities are modified slightly by density effects, but it certainly is helpful. First, because it gives us that link, allowing us to visualize what velocity means in thin section. And second, it points the way to go if we want rock type from seismics.
Exactly. For if we divide compressional velocity by shear velocity, Vp over Vs again, then, to a first approximation, we eliminate the rock fabric, and we eliminate the rigidity of the grains. Indeed, in any situation where we know the saturant is water, we identify the rock type by the bulk modulus of its grains.
And the rock type, of course, was one of our objectives on the wish list. So to the extent we can measure Vp over Vs, we have another way to get rock type, to supplement that from seismic stratigraphy, and a much more positive way than from compressional velocity alone.
Whereas, if we turn again to the saturant, compressional velocity alone is the key to detecting the presence of gas, thus supplementing the message from burial history. So if we have Vp over Vs in the reservoir below the spill point, and another measurement above it, then, in principle, we can eliminate the grain material and be sure whether gas is present or not.
Though without ever being able to say whether the gas is commercial or not.
So finally, if we know the saturant and the grain material through its bulk modulus, we also know its rigidity, and so can get a measure of the master variable. Now, the master variable, whether we use this suggestion or some other, is not in itself a direct measure of porosity, or cementation, or diagenesis. But that does not mean it is not a very fair measure of the appeal of a reservoir. A rock with a low value must have a very open fabric, whether that openness derives from the grain shape or the sorting or the absence of cement or shallow burial or overpressure. And a rock with a high value must have poor permeability.
So, loosely, it is some figure of merit for a reservoir. Let's do this. Instead of separate items for reservoir properties, let's just put in reservoir appeal and give it a qualified yes.
So, standing back and looking at this list, I'm going to say straight out that there is far more geology in the seismic trace than just structure. Our challenge is to winkle it out.
Are we pretending that the geologist's wish list is all solved? No, of course not. Even the big ticks here are sometimes tough or need more extensive data than we usually have. But the essential point is that the physics does allow the extraction of all these geological messages. We do have the tools. Where we fail, it is sometimes because of the geology, tectonic complexity, or because erosion has removed part of the picture. But often it is because of poor seismic quality or insufficient seismic resolution. And that is why we are discussing these geological matters here, so that all of us, field geophysicists, processors, interpreters, may see where the goalposts are before we specialize. In the field, we can jeopardize all of these objectives if the lines are in the wrong place or in the wrong direction or too short, if the group interval is too long or the arrays are too long or the spread is too short, if we do not plan in advance to measure VP over VS with a shear measurement or amplitude versus offset, if we use a source of inadequate bandwidth, and if we fail to get good static corrections from the first breaks or the upholes or a weathering crew. All of these possibilities can be lost forever in the field. Can be lost forever. You fellows in the field, you're important. The processors also must understand these objectives. We shall learn all the rules later, of course, but right now let's stress that different objectives need different processing. The optimum processing for structure is not that for stratigraphy. That for fault plane reflections is not that for stratal or unconformity reflections, and that for a gas-water contact is quite different again. Also very important is that geological thinking must go into the processing. Velocity picks and velocity smoothing must honor the stratigraphy and depositional environment evident on the emerging section. And the processing becomes more and more interactive. For example, we need velocities to get the structure right, and we need the structure before we know where to put the velocity measurement. Finally, the interpreter must extract all the geological messages in the seismic, harmonize them into an acceptable geological picture, forward model that interpretation back into seismic terms, and check that the result agrees with the original seismic data. So it really is a team effort. If you're the geophysicist in the field, let me never hear you say it. If you're the processor, think exploration objectives, not mere pretty sections. And if you're the interpreter, model it back. Well, there we are. The overall view, the grand view. From now on, we start to look at the details. The fieldwork first in the 300 series, then the processing in the 400, interpretation in the 500 series. In the 300 series first, you may care to look again at GP204, Introduction to Fieldwork, then on to 302, 303, and so on. I hope you find it all as fascinating as I do.